8.2 and 8.3 day 2, this is going to be continuation of the first day of notes where we're looking at hypothesis tests about proportions. Now the actual math and hypothesis test is fairly straightforward. The trickiest part is getting it set up correctly. And that comes down to writing the hypotheses and defining the parameters. So we're going to do a few more with those two steps alone just to get some practice with it. So example 1, it's been found that 50.3% of US households own stocks and mutual funds. A random sample of 300 heads of households indicated that 171 owns some type of stock. Does this provide evidence that the proportion of households that own stocks is rising? So the key phrase here is that it's asking, is this proportion rising? Okay, our parameter is what's the true proportion of households that own stock? Okay, so P equals the true proportion of US households that own stocks and mutual funds. The null hypothesis is that that proportion equals 50.3%, and the alternative is that it's rising. It's going up from 50.3%. Example 2, we have a survey that says 68.6% of the population owns their homes. We have a sample where 92 out of 150 people said, yes, I own my home. Does this suggest a difference from the national proportion? So our parameter, P equals the true proportion of people who own their home. Okay, the key phrase in this problem is difference. Okay, so we want to see, is it equal to 68.6%? That's the null hypothesis. Or is it different from that? In other words, is it not equal to 68.6%? In example 3, a rental car company believes that the proportion of customers who return their car with the gas tank filled is less than 25%. P is representing the true proportion of customers who will return their car with the gas tank filled. Null hypothesis is that it's equal to 25%. Alternative is that it's less than 25%. Remember, the null hypothesis always has to have an equal sign. The alternative is the one that has an inequality. So when it says less than 25%, this is automatically going in the alternative because it can't go in the null hypothesis. All right, with example 4, we're going to do a full hypothesis test. So to start off, we'll do our first two steps. We have data from the 1960s showing that 44% of the adult population has never smoked cigarettes. In 1995, we have a sample of 881 adults. 52% say they've never been smokers. Is that evidence that suggests that the proportion of adults who have never smoked has increased since the 1960s? P is the true proportion of adults who have never smoked cigarettes. Null hypothesis is that it's equal to 44%. This is the population we're comparing it to. This value is based on a sample of 881 adults. The hypotheses are always about the population. So P equals 0.44. It's asking, has it increased? So P is greater than 0.44. Moving forward, we're asked to find what is or are the critical values for this problem. Critical values for a proportion problem are always a z-score, just like we always dealt with z-scores when we were doing confidence intervals for p-hat problems. Now this critical value is based on an alpha. Okay, it's telling us alpha equals 0.01. If it doesn't give us an alpha level, we'll default to 5%. Okay, we also have to refer back to our hypotheses, notably the alternative hypothesis. So the important thing about our alternative hypothesis is that it's a right-tailed test. So what this is really telling us is that we have a right-tailed test and we have 1% on the right side. So whatever alpha level is, we're putting all in this tail right here. So we have 1% in that tail. We're going to look up a z-score that has 1% over here. We always look for the area to the left of that. So we would look up 0.99 in our table. We get a critical value of 2.33. Standard deviation, we're using this equation, radical PQ over N, and the P is from the null hypothesis, never from the sample. Okay, so all of our parameters for our normal curve are based on the null hypothesis being true. So 0.44 for P, 0.56 for Q. Sample size from up here, we get a standard deviation of 0.0167. Next, we want to find a test statistic, and a test statistic is just the z-score. So the z-score is based on the null hypothesis. So if the null hypothesis is true, and 44% of adults have smoked cigarettes at some point in their lives, what's the probability that we would see 52% in a sample of 881? So we're finding the probability of getting that 52% based on that standard deviation that we just found on the previous page, and we're doing a right-tailed test that was based on the alternative hypothesis. So we find a z-score for that 52% based on an actual true mean of 44%, divide by the standard deviation, we get this z-score, 4.79. That's a large z-score, it's off our table. We're going to use that to find a p-value. The probability of ending up in that tail is 0 plus. Now, based on that p-value, we're going to make a decision. And the decision is to reject the null hypothesis since that p-value is small, since it's less than the alpha level of 0.01. Let me give you a full explanation. So our entire test is based on an assumption that the null hypothesis is true. And the null hypothesis says that 44% of adults have smoked at some point in their life. So if that's true, we have 44% in the middle of our normal curve. The probability that we would see a sample of 52% or more in a sample size that's 881 large is really, really small. Okay, we found that it's 0 plus. So in other words, this would never actually happen. We would never end up this far from the mean, almost 5 standard deviations from the mean, okay, based on this being true. So because of that, we say what we saw would never actually happen if this was true. So we're going to conclude that this is not actually true. It's not 44%. Instead, it's gone up from 44%. That's what our alternative is saying. The actual proportion of adults who have never been smokers has increased from the 1960s. That's what our conclusion is. Okay, so we always make a decision about the null hypothesis. Either we have enough evidence to reject it, okay, and we do that when our p-value is small, because what we saw was really unlikely to happen based on the assumption that that's true. Okay, so we reject or fail to reject the null hypothesis, and then our conclusion is always based on the alternative. If we reject the null hypothesis, then we have sufficient evidence to suggest that the true proportion of adults who have never smoked has increased from 44%. Let's do another one. A local high school makes a change that should improve student satisfaction with the parking situation. Before the change, 37% of the school's students approved of the parking. After the change, they do a simple random sample, and they find that 83 out of 200 say that they're happy with the new parking arrangement. Does this provide evidence that the change was effective? So the parameter is the true proportion of students who approve of the parking situation. Again, keep in mind that this is just a sample, the 83 out of 200. If we talk to a different 200 students, we would probably get something other than 83 saying, yes, I approve of it. Samples vary, but the true proportion does not vary. Okay, it's going to stay at whatever the actual improvement level is. So hypotheses, null hypothesis that it's equal to 37%. The alternative is that the change was effective, meaning that more students are happy about the parking situation. So P is greater than 0.37. Next up, we want to find the critical value. And this problem doesn't give us an alpha level, so we're going to default to 5%. Our null hypothesis says that the proportion is increased from 37%, okay, which means we have a right-tailed test. We're going to put all 5% in this right tail. Okay, so 0.05 over here. We're going to find the z-score for that value, or for that cutoff right here, which means we're looking for 0.95 in that normal distribution table. We get a z-score of 1.645. Standard deviation is based on this null hypothesis value. The whole test is assuming that this is actually true. 0.37 times 0.63, divide by the sample size of 200, square root that, and we get 0.0341. Next up, a test statistic. So the test statistic is based on the sample. How unusual would it be to see this sample if the null hypothesis is true? So first off, let's find the p-hat. Okay, p-hats are used for samples where p is used for the true population parameter. Okay, so since we have a sample of 83 out of 200, our p-hat is 0.415. So if the null hypothesis is true, null hypothesis says 37% of students approve of the parking, would it be unusual to see 41.5% in that size sample? Okay, we're going to go to the right because it's a right-tailed test. So we want a z-score for that cutoff, 0.415 minus the actual mean of 0.37, divide by the standard deviation that we just found on the previous page, and we get a z-score of 1.32. Go to our table. Remember that the table always gives you the value to the left of this, so you have to do 1 minus to get our p-value. There's 0.0934, or 9.34% of the curve to the right of that cutoff. Now we're going to make our decision based on that p-value. The p-value was 9.34%, and for the purpose of this explanation, I'm just going to round that to 10%. Okay, normally we wouldn't do that, but it's going to help the explanation a bit. So our decision is fail to reject the null hypothesis because the p-value is too large. So when we do our test, we put 0.37 in the middle. And we said, if that's true. So in other words, if the student satisfaction hasn't changed at all, they made all these improvements to the parking situation, but let's say the students are just as unhappy as they always were. What's the probability that we ended up with a sample result of 41.5% or more? And it's about 10%. So in other words, even if satisfaction hasn't changed and it's still 37%, there's about a 1 in 10 chance that we'd take a sample, and just from natural sample variation, we would end up at 41.5% or more. In the same way as if we flip a coin 100 times, we're not always going to get 50 heads. Sometimes we're going to get 55 heads. Okay, sometimes we're going to get 47 heads. So this wasn't unlikely enough for us to say, yes, we have evidence that the proportion of students who are happy with the parking has increased. Okay, we need to see this percentage get lower for us to say we have evidence that this is not true. So because of that, when we write our conclusion, we say there's insufficient evidence to suggest that the true proportion of students who approve of the parking situation is greater than 37%. When it comes to these final two sentences, they're tied directly to your p-value. If the p-value is small, meaning below 5%, or if it gives you an alpha level below whatever that alpha level is, we reject the null hypothesis. Whatever we saw in our sample is unusual enough for us to say we have enough evidence to prove this null hypothesis is false. Okay, and when we reject the null hypothesis, that second sentence is always there's sufficient evidence to suggest that the alternative hypothesis is true. If the p-value is not small, above 5% or above the alpha, like in the last problem where we got a 10% p-value, we fail to reject the null hypothesis. What we saw isn't unusual. It's not unusual enough for us to say that null hypothesis is incorrect. When we fail to reject the null hypothesis, the following sentence is always there is insufficient evidence to suggest that the alternative hypothesis is true. The first sentence is always about the null hypothesis. We either reject or fail to reject that null hypothesis. And the second sentence is always about the alternative hypothesis. Either we have sufficient evidence to support that alternative, or we have insufficient evidence to support it.